This is the Fourier transform, and it is crucial for our battle against COVID-19. See, the virus has these tiny molecular machines, way too small for visible light to see. And if we can't see them, it's insanely hard to design drugs to stop them. But Fourier transforms made that possible. But what even is the Fourier transform? At its heart, it's a neat little idea. You draw a spinning arrow, then another, and another. Each one turns at its own speed and has its own length. Keep going and you can actually draw pictures with them. And in reverse, you can break a picture down into these spinning arrows and graph them by how fast each arrow spins, frequency, how long each arrow is, amplitude, and where each arrow starts, the phase. And that's what the Fourier transform does. And it solves the problem of visible light because it lets us do this. We can turn the molecule into its own Fourier transform using a physical process, and then use a computer to undo that and digitally reconstruct the shape. That's how we figured out what the virus looked like, that's how we designed better vaccines, and that's how we found out why certain drugs worked. And today, we're gonna build up to that. But first, how do you even do a Fourier transform on the molecule? The trick is to pack a bunch of these molecules together really tightly, freeze them into a solid crystal, and then blast them with X-rays. But why would this be a natural idea to even come up with? Whose bright idea is this? The idea actually came from chemists who weren't trying to fight pandemics at all. They all just wanted to study rocks. But curiosity is kind of funny like that. Sometimes it gives you the tools you don't really realize you'll need later on. When you shoot X-rays into a crystal, the atoms inside can interact with that X-ray since the wavelength is small enough. These interactions scatter the rays in a specific pattern. That pattern lands on the detector, and get this, it's actually the Fourier transform of the atom's layout. In other words, the scattered dots on the detector are like a shadow casted by the structure. If you read the pattern right, you can figure out what the original thing looked like. And this works great for biomolecules too. But why? And to that, we will go through a 3-part journey answering what creates an individual dot, how the intensity is represented, and how the frequency is represented. And all of this will show you how this elegant piece of math naturally pops out of biology. So, let's zoom into the crystal to rediscover this from first principles, and let's get this party started. Picture this. You've got a beam of X-rays hitting the crystal at an angle. Some parts of the wave hit the atoms right away, others travel a little bit further and reflect the deeper layers. Let me switch from the rays to waves and draw some atomic layers so you can see what's going on. Now, these waves bounce off because the X-rays interact with the electrons in the atoms. That means what we're really measuring on the detector is electron density. That will come back later, please keep that in mind. Most of the time, the reflected waves don't line up. They cancel each other out and disappear. But in just the right conditions, when the waves line up perfectly, they all add together and it etches a dark spot on a detector. This constructive interference is captured using Bragg's law. It's just some trigonometry really, but it was clever enough to win the Braggs a Nobel Prize in 1915. It is able to solve for the distance between the planes of the crystal atoms, and thanks to it, we can now use X-rays to see atoms inside of a crystal, indirectly but precisely. Great. Now that we know what each dot represents, let's move on to what the whole pattern tells us. Intensity and frequency. If you look closely at these dots, you'll notice something. They're not all equal. Some are darker and some are lighter. And spoiler alert, those differences, they do represent the intensities in the Fourier transform. But why? Well, I kinda played a trick on you. So far, I've been showing you this setup with a fixed point of view. But what happens if I take out the guides, tilt the crystal, say 45 degrees, and redraw the guides? Now we see two big differences. First, the spacing between the atomic layers, or planes, have changed. And that means the angle where constructive interference happens also changes. So this gives you the different spots. Second, let's imagine drawing a grid over these atomic planes. In the original view, the grid cuts through 3 atoms. In the tilted view, however, only 2. That's fewer electrons for the X rays to bounce off of, so the reflected wave is weaker. That's why some dots on the detector are brighter than others. In other words, more electron density equals brighter spot. And here's the cool part. This works no matter how complex your molecule is. The X-rays don't care what atom they're hitting. They just see electron clouds stacked in repeating layers. So, when you rotate the crystal, you're slicing through different planes. Some slices hit more electrons, some hit fewer. The result? A bunch of spots on the detector, each with their own intensity. And that intensity, well, that's the same thing as the amplitude in the Fourier transform. And that answers that question. But what about frequency? It's been staring at us the whole time. Imagine slicing the crystal at different angles. Some cuts hit a lot of atoms, frequently, others not so much. Well, that's your frequency. Each angle of the slicing maps to a different spot on the detector. And now, to figure out the original structure, you figure out which dot comes from which plane and how strong each one is, and you just add them back up together. Just like how you can add arrows rotating at different frequencies and amplitudes together to reconstruct an image. And that is why the Fourier transform shows up in biology. But there's something missing. Remember how each spinning arrow in the Fourier transform has 3 parts? The speed, the size, and the starting angle, also known as phase? Well, our detector only gives us the amplitude. It tells us how strong each arrow is, but not the starting angles. The missing piece? It's known as the phase problem. And without phase, you can't perfectly reconstruct the original structure. Scientists have clever tricks to estimate it, but still, this is one of the reasons why we can't just use X-rays for everything. But a bigger problem resides in the fact that some molecules don't even form crystals, and others are just way too fragile or dynamic. So, what then? Well, scientists didn't stop. They invented entirely new ways to see molecules. One of them is called Cryo-EM. You freeze a bunch of molecules and take thousands of blurry 2D pictures from different angles. You can actually use the Fourier transform to get rid of this graininess to reveal the important details, because grainy noise is higher in frequency. The other is NMR, or nuclear magnetic resonance. Instead of a picture, you get a signal, a messy mix of frequencies from the atoms in the sample. But here's the cool part. You can untangle that signal using, you guessed it, the Fourier transform. It's like hearing an orchestra play at once and separating out the sound of each individual instrument. And all of this illustrates what I find beautiful about math. This one equation isn't just about spinning arrows, X-ray diffraction, cryo-EMs, or NMRs. It embodies all of them at once. And that's the power of math. You take one simple idea, and then suddenly it works everywhere. The power of abstraction. But what does this power mean for us? Well, we've obtained the structures. Let's see how this added atomic perspective impacted our fight against COVID-19. If you've noticed in this video, I haven't really gone too deep into the math behind the Fourier transform. Although I believe it's a very beautiful piece of math and the deeper connections to crystal diffraction is very fascinating, it really would have been too much information and needed a lot of prerequisites. But with my sponsor today, Brilliant.org, you get to boost that prerequisite step. Brilliant helps you get smarter every day with thousands of interactive lessons in math, science, programming, data analysis, and AI. Brilliant helps you build critical thinking skills through problem solving, not memorization. So, while you're at it building real knowledge on specific topics, you'll also become a better thinker. Learning a little every day is one of the most important things you can do, both for personal and professional growth. In this video, one of the prerequisites to grasping the formula for the Fourier transform is calculus. So, you can use Brilliant's newly updated math courses to help you establish a strong foundation in algebra, and then build on that to conquer calculus and beyond, with an emphasis on problem solving and reasoning throughout. You will discover all the algebra you can already do but haven't realized yet, strengthen your logical reasoning and problem solving skills, and develop your mathematical intuition and fluency with visuals that bring these core concepts to life. With this, you will have the power of abstraction math gives you easily within reach. To try everything Brilliant has to offer for a free full 30 days, visit brilliant.org/nanorooms or scan the QR code on the screen, or you can click on the link in the description. You'll also get a 20% off on our annual premium subscription. This is the power this perspective gives you. Imagine you're a mechanic, but you're blind, can't feel, taste, or smell anything. You can only hear a nice click when things all work together. That's biology for you without these structures. The mRNA vaccines we are injected with encode for a piece of the virus, in particular, the structure of the spike protein. The immune system can remember the structure of the spike and recognize and attack the virus once we are actually infected. Great, we can just steal the code for the spike directly from the genome of the virus and include it in our vaccine. But not so fast. Upon examining the structure of the spike, scientists found that it changes when it enters the cells. It sheds its important parts and becomes extended. Your immune system will learn to recognize this form instead, not the one that's active in the viruses. Luckily, this is actually a problem that's known to them from previous structural studies of MERS and SARS. The simple trick is to add a few specific mutations to the spike, and the spike won't change structure. And that clever trick is what gave us vaccines from Moderna, Pfizer, and more. A discovery from a past virus, built on structural insight, helped us prepare for a new one. That's the power of standing on the shoulder of giants. But structures of molecules don't just give us the tools to deal with the present, they help us prepare for the future too. And it starts with simply satiating curiosity. Take Remdesivir, one of the first antiviral drugs used against COVID. It wasn't actually designed for COVID. It was originally designed for Ebola. Scientists had a hunch. Well, what if we mess with the virus's building blocks? See, viruses like SARS-CoV-2 have RNA genomes, and they need to copy that RNA to make more of themselves using this machine called an RNA polymerase. Remdesivir kind of looks like an A base, the letter A in ACGUs. So, the idea was this. What if we sneaked in a fake A to jam the copying machine? And it worked. But nobody was quite sure how it worked. Why does the copying machine fail? And why, weirdly, do all these broken strands stop exactly 3 bases after Remdesivir gets added? So scientists did what they did best, and you guessed it, they just looked at the structures. They captured Remdesivir in action with the copying machine frozen in action. With the structural data, let's just say, pictures are worth 1,000 words. So let me just show you. The molecule jams into the enzyme just fine. But 3 bases down the line, it collides with this tiny hinge inside of the viral RNA polymerase. That hinge pushes back, and the machine stalls out. And that's why the virus can't finish copying its RNA. No one designed Remdesivir to do precisely that, but now, because we can see what happened, we can now start designing the next generation of antivirals with purpose. That's the power of structural biology. It takes off the blindfolds to our senses so that we can better fix the car. So, did this 218-year-old equation solve COVID? No, but it played a crucial part. Fourier's equation was indeed powerful, sure, but it would not have been possible without the curious chemists, the structural biologists, the people who built on each other's works layer by layer without knowing where it might lead. And that's the point. That's why we fund basic research, not because we know what it will lead to, but because we don't. Curiosity is unpredictable, but it's the best chance we have at being ready when the world needs us. So, maybe, take a walk with a friend, talk about something weird, chase a question that doesn't have a purpose yet. You never know. It might just change your life, and 200 years later, someone else's too. Thank you immensely for watching.